So exercise related to entropy. So this is a qualitative analysis, like we will do calculation to work out the entropy changes. So in this question is about the sucrose, the chemical commonly known as a sugar. Some thermochemical data for sucrose and oxygen are given in the table. The standard entropy of a sucrose is given, which is 392.4 joule mole inverse Kelvin inverse. The standard enthalpy change of a combustion is also given, which is if you burn 1 mole of a sucrose, how much energy it released. And standard entropy of the oxygen is also given, which is 102 joule mole inverse Kelvin inverse. The equation for a complete combustion of a sucrose is shown. Calculate the standard entropy change of a system. So how we calculate the entropy change of a system? The entropy change of a system is calculated by using a formula product minus the reactant. So if we subtract the total entropy of the product from the reactant, from a balanced equation, the equation must be balanced. So we will get the total entropy of the system. So we have 12 moles of carbon dioxide and we have 11 moles of water molecule using a data given in the table and your data booklet. So in exam, you will have either the table will be there or the data booklet. So using a data booklet, what you will do, you will find the total entropy of a carbon dioxide and water molecule because that is not given in the table. Only the entropies for oxygen and the sucrose are given to us. So we will use the data booklet to work out the values. So from data booklet, when you find the value for carbon dioxide, for carbon dioxide, it is, can we just divide the enthalpy change of a combustion with the temperature and use that the product side? No, if you use this formula, because we need only for system, we don't have the, if you are using this formula that the total entropy, which is equals to entropy of the system plus entropy of the surrounding. Why this formula is not applicable? Because I don't know what is the total entropy. And delta H and T can be used because it's a standard. So we can get this, but we don't have the total entropy. So that's why two unknowns will be there. One is a system, another one is a total. So the formula which you will use whenever you need for system, it is a total entropy of the product minus the reactant. So system is the total entropy of the product, standard entropy of the products minus the standard entropy of the reactant. Delta H is given to us. If you see, this is the delta H which is given to us in the question, the combustion of the sucrose. So what is the product? The product is carbon dioxide. When you check the data booklet, it is 213.6. In exam, you will have the data booklet. So multiply by 12. So this will be multiplied by 12 plus for a water molecule or H2O, it will be 69.9. And how many moles are there? Multiply by 11. That is the product minus the reactant. What are the reactant here? 1 mole of a sucrose. So that is 392.4. plus for oxygen it is 102.5, and how many moles of oxygen are there? 12. So this will be multiplied by 12. So the product minus the reactant will give us the total entropy of the system. Now, if you see for oxygen, yes, that is right. For oxygen, this is for half mole of oxygen, like total entropy for half mole of oxygen. How many moles of oxygen are there? 12. So if half mole of oxygen is 100, because when you read the question, it's written half mole of oxygen. Half mole of oxygen is this much. So 12 moles of oxygen, how much it will be? It will be again multiplied by 2. So means it will be 24 times. Is it clear? Why it is 24? Because for a half mole of oxygen, it was 102. But we have 12 moles of oxygen. So how we'll get here at 12? Means this will be multiplied by 24. 24 multiplied by half will get 12. So means this should also be multiplied by 24. So the number here will be 24. When you simplify, this will give us the entropy change of the system, which is 479.7. Is it clear, this one? And we get a positive answer. So this entropy change of the system is positive. Any doubt in this? And how you can use a data booklet? So we worked out the entropy of the system. Then how to work out the entropy of a surrounding? Entropy of surrounding is minus delta H over T. So we need the values here. So if we need the surrounding is minus delta H divided by T. The value of a delta H is itself, because it's a combustion exothermic, so it is, but it is in kilojoule. So what we will do, this is minus 5, negative sign for the formula, like this delta, negative delta H over T is a formula. Then the delta H itself is negative, so we wrote 5639.7 and then multiply by 1000. Why multiply by 1000? To convert into joules. And then divided by temperature, which is 298 Kelvin. So this will give us the answer in joule mole inverse Kelvin inverse, which is plus 18925. So the final answer will be plus 18925 joule Kelvin inverse mole inverse. And if I need the total, so to get the total, it will be a system plus the surrounding. System we calculated in the first part, surrounding we calculated now, and we just sum them to get the total. So it was the system we calculated 479 plus the surrounding was 18925. So when you sum them and use the decimals as well, like at least 1 decimal or 2 decimal places, so you will get about 19404. 19405, okay, 404. So 19404, and the unit will be joule, mole inverse, Kelvin inverse. And because we are getting a positive answer, so what does it mean? This reaction will be spontaneous, or it will be feasible. State and explain the effect, if any, on increasing a temperature of a surrounding, increasing a temperature on entropy change of a surrounding and total entropy, the extent of reaction. See, this reaction is exothermic. So the total entropy is the entropy change of a system which won't change, because entropy change of a system depends on the condition, like mainly if we carry out the standard entropy changes, so it is done at a standard condition. So it depends on the reactant and the product rather than the conditions. So this won't change, this remain constant. And we have minus delta H over T. And this reaction is itself is exothermic because the value of a delta H was negative. So mean this value will be negative. So entropy of the system plus, because minus negative times negative, so it will be positive, plus delta H if over T. If I take T as an LCM, so it will be T entropy of a system, or if we keep it same like this. Now, if I'm increasing a temperature, so I'm increasing this factor. So what will happen to this, the entropy of the surrounding, because delta H value is a fixed, temperature is increasing, so the total entropy of the surrounding will decrease. Because the entropy of the surrounding is minus delta H over T. So if the T value is increasing, entropy change of a surrounding will decrease for us. And as the entropy change of a surrounding decrease, total entropy is a system plus the surrounding. So the total entropy will also decrease in this case. So how you relate, like what should be the structure of your answer? Like entropy change of a surrounding, which is minus delta H over T. So as we increase the temperature, and delta H is negative, so the entropy change of a surrounding is delta H over T now. As the temperature is increasing, so the entropy of a surrounding decrease, or it will become less positive, we can also say. And the total entropy will also decrease because it is a sum of system and surrounding. So the total entropy will also be less positive. This can never be negative. We will never get a negative answer. It will be less positive answer. So this reaction, exothermic reaction, remains spontaneous at all the conditions. If a reaction is exothermic, it will always be spontaneous at all the temperature. But the feasibility of the reaction, it will be feasible, but the change in entropy will be smaller. How we mentioned that the delta H become positive because the reaction is exothermic. So we have the entropy of the surrounding is the formula to get the entropy of the surrounding is minus delta H over T. This delta H is negative for exothermic reaction. So negative multiplied by negative will become positive. So this will become delta H by T. And if the temperature increase, the entropy of the surrounding will decrease. And it will be positive, but it will be less positive. And if the entropy of a surrounding is less positive, the total entropy will also be less positive. Is it clear? Then we have icing sugar can be hazardous when it is being finely powdered in a factory. Explain why sucrose is a stable at room temperature in spite of your answer to part 3, but its manufacture is hazardous. So If you read the whole question, when we compare, because I mentioned icing sugar can be hazardous when it is being finely powdered in a factory. So when we make like powder form, when we are crushing it in, it can be hazardous. And explain why sucrose is stable at room temperature in spite of your answer to part 3, but it is manufactured is hazardous. Like, what could be the reason why when we are manufacturing sucrose is hazardous, but it can be stable? So first thing, when the reaction is exothermic, when we define the reactant, we use the term thermodynamic stable, and we use the term kinetic stable. What is the meaning of the term thermodynamically stable? The term thermodynamically stable means the reaction will occur, like, for example, if we have calcium carbonate, CaCO3, the CaCO3 can decompose into what? It can decompose into calcium oxide and carbon dioxide. And this reaction is endothermic. Endothermic reaction, the reactant have less energy and the product is having high energy. So, which is more stable thermodynamically? So, the one which is having less energy. So, means the calcium carbonate will be more stable, or calcium carbonate will be thermodynamically stable. So, where in an energy profile diagram, the one which hold the less energy is called thermodynamically stable. Same thing, we use another term. Let's say we have a reactant forming a product. So which is thermodynamically stable here? The product is thermodynamically stable in terms of exothermic reaction. But the reaction is not happening. If the reaction is not happening, reaction should occur, but reaction is not happening. The product is thermodynamically stable, but still the reaction does not happen or occur. So what we call those reactant, we call those reactant as a kinetic stable. So like example, the best example to understand the kinetic stability, the mixture of the petrol and air or oxygen. Petrol can burn if you take a container, or you and transfer, or you take a petrol and transfer that into a small beaker, it won't catch fire by itself. But the moment it is ignited or any spark is there, the whole petrol will burn. So the petrol is kinetically stable because the petrol should burn and produce carbon dioxide and water, but it is not burning by itself. There is some energy we need to start up a reaction. So what we call those type of reactant, we call them as a kinetic stable. So here this answer, when we structure this answer, we will relate the kinetic stability, because the question is explain why sucrose is stable at room temperature in spite of answering part 3. Because when you see the combustion of a sucrose, the combustion of a sucrose is exothermic. When we have an exothermic reaction, means sucrose will be the reactant and carbon dioxide and water will be the product. So sucrose is not forming carbon dioxide and water by itself or not catching a fire. So what could be the reason for that? It means the sucrose is kinetically stable. Or we can also say we need some activation energy to start up the reaction. That is not provided. That's why the reaction does not start. So sucrose is kinetically stable because the activation energy for this reaction might be higher. And why it is hazardous? Because when it is crushed, the particle size decreases. When the particle size decreases, the surface area will increase. And if it has a large surface area, it can burn easily. So, why its manufacture is hazardous? Because if you read the question, the icing sugar, because when it is being finely powdered in a factory. So when we do powdered form, it means we crush it or a small surface area. So small surface area means, large surface area means it can have a higher rate of the reaction. That's why it will be hazardous. But why it is stable? Because it may have a high activation energy, or the conditions are not feasible for this sucrose to convert into carbon dioxide and water. So whenever we refer at kinetic reactants of the exothermic reactions are always kinetically stable. Means they should form a product, but they're not forming a product because maybe they need some energy to reach activation energy. And the reactants of the endothermic reactions are always thermodynamically stable. Is it clear, this part? Suggest two risks which are associated with the high levels of sucrose in a diet. This is how is stable and hazardous here. How we relate this stable and the hazardous. Look, we have a sucrose. The question is why sucrose is stable at room temperature, like why sucrose is not converting into carbon dioxide and water. So the reason is that the combustion of a sucrose is exothermic, but to reach the activation energy, maybe the activation energy is higher. That is why the sucrose does not convert into carbon dioxide and water by itself, because it needs some energy to reach an activation energy, or activation energy is higher. And then why it is manufactured is hazardous, because when it is icing sugar can be hazardous when it is being finally powdered. Like when we crush it or fine powdered form, it will have a large surface area. Large surface area increases the rate of the reaction. So maybe one particle, if it start up the reaction, it will release energy and all the particles will gain the energy which is released, and it will start up a chain reaction. But when it was a large piece, it has to change whole by itself. So that's why the large piece is not hazardous, but the finely powdered is, because it can easily catch fire because of a large surface area. Is it clear? Then the last part is mainly like two risks associated with a high level of sucrose in the diet. Biology style question, like you can mention. In exothermic reactants, no. In exothermic reaction, the reactants are kinetically stable. And in endothermic reaction, the reactants are thermodynamically stable. Yes, it can cause diabetes. So if we have an exothermic reaction, the reactant have high energy, product is having low energy. Because the one which is a low energy, we call thermodynamic. So product is thermodynamically stable. But the reactant is not forming a product, it is kinetically stable. Because it might need enough energy to, or it does not have enough energy to reach activation. But in endothermic reactions, the reactant form a product. So the reactants are thermodynamically stable. Means you have to supply energy to form a product. It won't form a product by itself. So kinetic stability is always used for the term when the product should form, but it is not forming. Still we see a reactant, that reactants are not forming a product. So this is one of the questions from exercise entropy. I will share this exercise and you will solve and submit as a weekly homework. Any question or doubt?